Welcome back. So, last day we have talked about the idea of calculation of page rank, and we have also computed explicitly the formula that goes into calculating the value of page rank. Okay. So, in the original page rank algorithm, alpha was set to 0.85 and beta was set to 1. Okay. It is not known why these parameters were chosen, but possibly the best results, the best ranking results in terms of user satisfaction was probably obtained based on was probably obtained if the constants were set like this. Okay. So, now today we will try to dig a little bit deeper into this idea of page rank, and the question is like what process, what background process of like related to the user actually can result into this formulation of page rank. That is the question that we are going to ask. So, is there an underlying process that actually really mimics the formula of page rank? That is the question that we are going to ask and trying to see if there is a satisfactory answer to this question. This brings us to what we call the random surfer model, or interpretation of the web surfing as a random process. Okay. So, if you look at the slides, the steps of the algorithm are very simple. So, initially every web page is chosen uniformly at random. Okay. You choose any web page. So, you suppose you are on the World Wide Web graph and you choose every individual web page, you choose every individual web page, that is every individual node with equal probability, that uniformly at random you choose one of them. Now, again look at the slides. So, with probability alpha, perform random walk on web by randomly choosing hyperlink in the page. With probability 1 minus alpha, stop the random walk and restart web surfing. Page rank is nothing but the steady state probability that a web page is visited through the web surfing. Okay. So, the idea is very simple. So, what you do here, you are standing on a node on the network. Now, from that node you move to any one of the neighbors of that node uniformly at random. That is what is we refer to as random walk. Now, this you do with some probability, say alpha, and with the other probability 1 minus alpha, you stay back in that particular node and you read the contents of that particular page. That is the probability 1 minus alpha. So, now if you do this process, if you continue doing this process for a quite long time, then the stationary probability that you will land up on a particular node is what is the page rank value. Okay. That is what actually corresponds to the value of the page rank. So, as I said, there are two important things to understand. One is the random walk, which I have already tried to explain you. We will see a example to make things better, and there is this steady state probability. So, these are the two important keywords that we should get to know while understanding random web surfing. So, the first of this is the idea of random walk. So, again look at the slides. So, let us say you have an adjacency matrix A of this form. So, from this adjacency matrix you convert it to a probability matrix, a stochastic matrix, where you normalize the contents of each row by the sum of that row. That is, you are basically normalizing the each cell by the degree of that node. Okay. So, you normalize the matrix and you get a transition matrix. This is what is called the probability transition matrix or the row stochastic matrix. Okay. So, that is basically Aij, the content of each cell, by sum of I Aij. Now, given this structure, suppose you have the original graph, the graph corresponding to the adjacency matrix A in this particular case would look like the one that I am pointing by the mouse. Okay. Now, when you translate this graph into a transition matrix, the values on the edge correspondingly change, okay, as you see in the transition graph. Now, given this probability matrix or the transition matrix, this stochastic row stochastic matrix or the transition matrix, the task that you have to do is the following. Suppose there is a random walker standing at the node red node A, okay, here. So now for this walker there is only one place to go, and that is this particular node at this time point t0. So it moves there. Now from here there are again only one possibility, and that possibility is to come to this particular node here. So the random walker moves from this particular node to this particular node, okay. That happens at time instant 2. Now from here the random walker has equal chances. See, there is a probability half of going to this node and there is a probability half of going to this node back. So the random walker can take any one of these two paths, okay. So probably it has taken it can go here, either here or it can go here, each one with probability half. So in this way you can try to simulate this process. This is the process that we were talking about. This is the process of web surfing. So every time the walker with some probability alpha jumps into one of the other web pages with 1 minus alpha stays back in that particular web page. So that is kind of simulated in this slides. So now given this situation we can always write the page rank equation back. So what happens? So now the probability that the walker stays on the page, that is your inherent popularity, right? This would correspond to my beta in the expression for page rank that we have already written. So basically here beta is nothing but it is equal to the 1 minus alpha probability of the random surfer model, okay. So my beta is the probability of staying in that particular node, because that is my inherent centrality, okay, and that is in this random surfer model that is set to 1 minus alpha. The other part remains as alpha. So now then you can write xt, the expression for xt, that is the popularity value, as alpha a d inverse x t minus 1 plus 1 minus alpha into the vector of all ones, right. So you can write the expression, the page rank expression once again. I have written the same page rank expression as we wrote earlier, but now substituting beta with 1 minus alpha. Now this actually has an advantage. We can further simplify the formula. If we assume that we are working on the stochastic matrix, that is the transition matrix, where everything is normalized between 0 and 1. So it is a stochastic matrix, all the values are probability values. Then the sum of all xt's, actually I 1 to n, these values, the sum of all the entries for all the xt values. So each node will have an xt value, okay. So each node will have a popularity value, and the sum of all these popularities is suitably rescaled because we are working on the stochastic matrix. So that is why this sum will be equal to 1, okay. So given this, what we can write? We can rewrite the expression for xt as xt is equal to alpha a d inverse x t minus 1, and we play a small trick out here, 1 minus alpha into 1 transpose x t minus 1. Note that 1 transpose x t minus 1 is nothing but 1, because you are multiplying a vector of all ones with the entries of the x t minus 1 vector. So x t minus 1 vectors will have the node popularity values for each of the individual nodes. Now if you multiply these values with the vector of all ones, so it will be sum of all these values. Basically it will be sum of all these xt values for each individual node, and this sum, as we have seen, is equal to 1 from the previous. Let us call this equation 1. So this part actually comes from equation 1, right. So basically if we know that the sum of all the popularities values always remains between 0 and 1, in each step whatever you do, it is only the relative ordering of the x values changes, but it is the sum of the values always remains 1. Then 1 transpose x t minus 1 should be equal to 1, because you are making a product of the of a scalar of all of a vector of all ones with the individual x t values. This will result into sum of all the x t values, which is equal to 1. Okay. So, now if we consider P is equal to alpha A d inverse plus 1 minus alpha 1 1 transpose, then we can write if then x t is nothing but P x t minus 1. Okay. And this P matrix is called the probability transition matrix of page rank. The P matrix is called the probability transition matrix of the page rank algorithm. And what we are interested in? We are interested in the limiting values of this matrix. Say for some m limiting to tending to z infinity, we say this should converge. Okay. The P transpose, the transpose of the probability transition matrix raised to some power very. So, basically what you are doing, in each step you are powering this transition matrix and you are continuously doing this power. So, as we were doing in the original eigenvector centrality case. So, you are continuously powering this value. Okay. So, in the first step you have p, in the next step you have p square, in the third step you have p cube, and so on and so forth, and after a point in time this transition matrix does not change any further, and that is the point where you get the stable set of the stationary distribution of the popularity values. Okay. So, at large m, at m tends to infinity, we receive the stationary distribution of the popularity values. So, that is how one can reinterpret the idea of page rank formula as a random process of web surfing. Okay. So, once this idea of page rank came into business, there were a lot of other people who started working in order to make this idea even better and better. Okay. So, and one of the most notable works in this area was by a famous scientist called John Kleinberg, who in 1999 proposed the idea of hubs and authorities, in the famous journal of ACM. Okay. So, the idea again is very simple and it is just an extension of the page rank idea, initial page rank idea, but it is actually found to be more impactful. The results that are obtained using the hubs and authorities idea are found in general better than the page rank approach. Okay. So, the idea is very simple. There are two different types of nodes. So, basically like the page rank was having only one popularity value, and that was based on the in degree of the nodes. If you remember correctly, the node C that I showed you earlier in this slide was having a very high popularity value by virtue of having a in degree from B. Okay. So, the page rank idea is mostly based on the concept of having high in degree values. Okay. Having in degrees from highly popular nodes. Now, Kleinberg extended this idea to also the out degrees, and there comes the concept of hubs and authorities. So, there are two types of entities, hubs and authorities. So, the hubs, as the name suggests, are links to popular content or popular nodes in the network. Okay. Whereas, the authorities are themselves popular or authoritative nodes themselves. So, this is easy to understand in the context of citation networks actually. So, basically in a citation network, a hub node would be such a node which contains references or out degree or pointers to all important or authoritative papers. Okay. So, such cases of hubs in citation networks would be analogous to survey or review papers. So, hubs in citation networks would be basically analogous to good survey or review papers. Okay. Whereas, authorities in citation networks would be analogous to important or seminal papers describing a method or an algorithm. So, in other words, the paper which actually describes the shortest path algorithm by Dijkstra would be a authoritative paper, whereas in general survey papers on the subject of graph theory which actually refer to such papers of Dijkstra, such papers like that of Dijkstra would be a example of a hub node. Okay, in the citation, in the context of the citation network. So, now the question is, given the structure of the network, how one should try to quantify the hubs and the authorities. So, basically the from the definition itself it becomes clear that for a hub what is important is the out degree. The out degree is more important, whereas for an authority what is more important is the in degree. So, now based on this intuitions we have to develop a quantitative metric for both hubs and authorities. Okay. So, the idea is very simple. Now, the hub score is defined by the sum of the authority scores of all the nodes pointing to the hub node. Similarly, the authority score pointing out of the we will see an example out of the hub node. Authority score is defined by the sum of the hub scores of all the nodes pointing to the authority node. Suppose there is a hub node A here, okay, and it is pointing say to 5 other 1 2 3 4 1 2 3 4 5 6 other nodes, okay. And suppose the authority scores of each of these nodes is defined as is given by say A1 here, A2 here, A3 here, A4 here, A5 here, A6 here. So, the hub score of the node A, if we denote it as HA, should be equal to A1 plus A2 plus A3 plus A4 plus A5. Okay. Similarly, the authority score can be computed. Suppose there is this node B, which is being pointed to by some hub nodes, and say each of the hub scores of these hub nodes are H1, H2, H3, H4 and H5. Then the authority score of the node B, okay, let us call it AT of node B, is expressed as the sum of the hub scores. H4 and H5. Okay. So, this is how you express the hub and the authority scores, and like PageRank, it is actually a recursive definition. So, your hub score is dependent on your authority nodes, their neighbors, and it continues in this way. I have here, for simplicity, I have shown a first level example, but this is actually a recursive definition, just like that of the PageRank or the initial eigenvector centrality idea. Okay. So, then how to express this in mathematically or quantitatively? So, in matrix terms, actually you can write the hub score as x equals A transpose y, okay, where and similarly, so this is the authority score. So, basically authority score is given by x and hub score is given by y, and similarly you can write y is equal to B A x, just as we were doing in the previous examples for PageRank and general eigenvector centrality. So, the authority score is basically summed over all the hub scores, and the hub score is basically summed over all the authority scores. So, given these two equations, let us call this equation 1 and this equation 2 here. Given these equations, we can express x as alpha A transpose A x, right, and similarly we can express y as beta A transpose y, fine. So, that means the hub score is the principal eigenvector of the matrix. So, the hub score should scale as the principal eigenvector of the matrix A transpose, whereas the authority score is the principal eigenvector, should scale as the principal eigenvector of the matrix A transpose A. Okay. So, it is very simple. So, given the adjacency matrix, the directed adjacency matrix, you compute A transpose and A transpose A. Now, you compute the principal eigenvector of each of these product matrices, and each of them actually represents the hub and the authority scores correspondingly. Okay. So, now given these two values, what the steps of the algorithm are very simple, as I have already stated in the slides. So, look at the slides. So, there are basically 3 steps in the algorithm. Assemble the target subset of web pages from the graph induced by their hyperlinks and compute A transpose and A transpose A. There is a printing mistake here, one is A transpose A and the other is A transpose. Okay. So, basically the first step of the algorithm is for the induced web graph with adjacency matrix A, compute A transpose A and A transpose. So, this actually stands for the authority and this one stands for the hub. Okay. This is the first step. Next, compute principal eigenvectors of A transpose A and A transpose. Fine. So, we compute the principal eigenvectors of these two matrices. Now, output, the third step is output the top scoring hubs plus the top scoring authorities. So, now see, this is the interesting difference from the page rank algorithm. When we were ranking the nodes based on page rank, you would just return those nodes which are basically good authorities. You will miss the good hubs. So, now we are using this advanced calculations, we have now incorporated both the good hubs as well as the good authorities in our search results. We will stop here. Thank you.